Okay, now here we are in our R Studio. First things first, loading the necessary packages. Here is the PCA methods package, which has the algorithm implementation. Next, let's talk about PM 2.5 for a second. PM 2.5 is particulate matter. Loosely speaking, that is a really fine dust which diameter is 2.5 micrometer maximum. This indicator is commonly used to understand the level of air pollution. So the higher the value means that there are more dust in that area, so higher pollution. Our PM 2.5 data is from the Bogotá Air Quality Monitoring Network. I'll use the same dataset from my previous project, linked here for reference. Now we load the dataset. We load the dataset and save it as DF, then change the data type for the column date time, and rename one of the variables. That variable was originally ozone, but in Spanish, or maybe in Brazilian, I'm not sure. Anyway, this DF has the measurement for all stations in Bogotá. The list of the stations are here. But to simplify the project a little bit, I chose the readings from only one station, and that is the station LFR. So I named the subset A to make it consistent with the theory. Okay, let's run the cell. Here, by running the function str in R, we can take a glance of the subset A, and from this we can see that A has around 8,700 observations. This is an hourly time series for a year in 2021. So as we can see here, the date time here, the first value is this, and at 1 a.m. and then the next is 2 a.m., 3 a.m. and so on. There are other measurements other than PM 2.5, such as PM10, and then nitrogen monoxide, nitrogen dioxide, and so on. In this cell, I make the time plot for PM 2.5, the time series we want to impute. So here it is. Okay, so this is the time plot, and perhaps it's a little bit hard to see the gaps, but we can see one here. Let's zoom in. Okay, so like here, January 25, we have around 8 hours of missing values. A longer period of missing values occurred here on January 22. So this is January 22, but the next observed value is on January 25. So the missing value lasted for around 3 days. I also plot the scatter plots of pairs of variables in the dataset. Here we can see a clear and obvious correlation between PM 2.5 and PM10. We can see strong correlations among the nitrogens as well, like for example this one, NO and NOx. Okay, and then I tried to calculate the total missing values in this dataset. In A, we have 254, which is quite small, considering that we have 8,000 of observations. Let's see. Yeah, the missing values is only 2% of the whole subset of the whole matrix A. Okay, and then lastly, I just want to see if the missing values occurs more frequently at a certain time. If we have 254 missing values and we have 24 hours a day, that means if we want to have a completely random missing values, then each hour should have around 10 occurrences of missing values. But here we can see that the missing values occur the most at 7 a.m. and at 12 p.m. And I think the NAs generally occur more frequently in the evening than in the midnight. Okay, now that we have seen the data, we need to do the final preprocessing so that our matrix can be processed by SVDImpute right away. There are several requirements we need to check. Like for example, we need a numeric matrix. So we cannot have a vector of characters or any other data type. That's why in this line 75, I removed the last two columns in that matrix. They are the station identifier and the date time. The next requirement is that we cannot have rows with all missing values. So like I illustrated earlier in the theory section, we cannot have a row with all orange boxes. And to check that, I make a little function in the next line 76. And well, let's run this first and then run the function. And then here we can see we have 22 such rows. And for these rows, we're going to do forward filling. That is in this line. Okay, now this requirement is already fulfilled because we don't have any more rows with all missing values. And then the next requirement is that we cannot have a column with all missing values. So basically we cannot impute a time series that is originally empty. Alright, I guess that makes sense. And even though I haven't shown you, okay, let me show you the matrix A now. After removing the last two columns, we can see that we don't have any column with all missing values, because if that's the case, we will see a column of all NAs right from the first page. Here are the first 10 rows of the matrix, and other than these two NAs, we have all the data. So that requirement is already fulfilled. Okay, so now our matrix is ready for imputation. Here I showed you the non-recommended way, that is by using the SVDImpute function right away. So running this won't give us any error. Let me run this line only. See, it gives us the change in estimate, which is, by the way, the total change. It can run the imputation normally and no error. And we can even look at the summary of the object. But we won't get anything. We won't get the imputed data. So to get the imputed data, we have to run the object of the imputation, which is here, direct imputation, and we put it into the complete observation function. As we can see, running this line will give us nothing. And yeah, that's why we cannot impute it using SVDImpute function. Now, the right way to do it is by using the PCA function and then put the SVDImpute as a value in the method argument. And then this is a little bit different from what I showed you earlier in the slides, but I use the CV and type arguments. Okay, and by the way, this scale argument is for scaling the data. I'm using the Pareto scale method, that is the square root of univariate scaling method. And then the argument for centering the dataset is also here actually. It's also available, but its value is true by default. So I'm not changing that. That's why I don't write it here. But for the scale is none by default, so it doesn't do any scaling. But I decided to do one. I decided to do Pareto because I thought this is basically like PCA, principal component analysis. So I thought, well, the standard practice in PCA is to standardize and basically normalize. So take the mean and the variance out of the dataset. Okay, now what is the CV argument? We don't know how many principal components we want to take. So I'm going to use cross-validation to determine that. And the metric to compare the models is Q squared. So Q squared is the cross-validation version of R squared. R squared is the variance, the proportion of variance explained by the principal components. Okay. And then the type here, this argument is actually for the argument in the Q squared function. I'm using the impute because we have missing values in our input matrix A. Okay, let's run this. Again, the change in estimate here, I don't know if it's clear. Oh, okay. So the change in estimate here is the total change in estimate between the last matrix and the previous matrix from the previous iteration. All right, now we can gain some information out of complete PCA object. The first is sdef. By running the sdef function, we can get the eigenvalues. And we can see that the eigenvalues are sorted. So the first principal component is the most important eigenvector because it has the biggest eigenvalue. Okay, and then we can also plot it. We can also plot the object right away, and this is what we get. The R squared and, like the bar plots of R squared and Q squared, but I'd like to do it like this. Okay, so here we have 3 lines to plot, but actually the first 2 lines are exactly the same. So I just want to show you that we can get the Q squared values in 2 ways. The first is by running the CVStat function. We can do that because we already specify the CV in the PCA function. Okay, and then the second way is the more direct one, that is by running the Q squared function. And see, the type impute here is exactly the same as here. And then nrun CV is the number of CV iterations that we want. The default value is 1. I am aware that the better practice is to have more than 1 run. And I tried to run it 5 times, but I get the same result. So let me show you. Let's say that we run it 5 times and see the result. Okay, now we have the Q squared scores for each principal components in each iteration. So the columns represent the iteration, and we can see that they are exactly the same. So that's why I run it only once. Now let's take a closer look at this plot. And so, as we can see here, the Q squared scores is exactly the same, no matter which function we run, right? So I'm going to remove the gray line now so that we have only 2 lines, the black line, which denotes the Q squared scores, and the red line, which is for the R squared, the cumulative R squared to be exact. And then the x-axis, this is for the number of loadings or the number of principal components. Okay, so when we have only one principal component, that single principal component can explain 66% of the whole dataset. This is what the R squared is telling us. Okay, and then for the Q squared, this is like R squared, but the cross-validation one. The lower the Q squared, the less meaningful the principal component in trying to explain the whole data. And looking at this plot, I want to use 2 and 3 principal components later. So I want to try using 2 different values for k, that is 2 and 3. Why 2? Because using 2 principal components, we can get the highest Q squared, that is 0.61 here. But using 3 principal components, even though the Q squared value drops a little bit, we can get quite high or like decent cumulative R squared. So the 0.92 here means that using 3 principal components instead of using 7, we can explain 92% of the whole dataset. That means if we use 3 principal components or 3 variables, we have a better chance of getting good imputation. Why not 4? Because using 4 principal components give us a quite low q-squared. Yes, we can see the q-squared from using 3 to 4 principal components drop a lot. And the r-squared, the cumulative r-squared, doesn't improve that much. So yeah, I'll stop at 3. Okay, now the next thing I'm going to do is running the PCA function twice. The first is using 3 principal components and then 2. After running the PCA function, I store the object in PC3. That means I'm using 3 principal components, and then put this object into the complete observation function to get the imputed data. Let's run this chunk. And then, yeah, we can get the summary of the object. This is quite similar, similar with if we just run the PC3. Anyway, I also add the line plot of this imputation to our time plot earlier, but we're going to save that for later. Now, I want to get some insights from this object before looking at the imputation plots. Okay, so first of all, we can get the r-squared cumulative from PC3, and we can just plot it. This is actually similar to this, so the cumulative r-squared 0.67, 0.85, and then 0.93, and yeah, that's what we have in this plot. Okay, and then we can also plot the principal components side by side by using this function. So we have different names for principal components so far, right? Like the columns of matrix V, and then the loadings, and then principal components. Another name for that is the new coordinate system. Now recall that the columns of matrix V are orthogonal, so they can be seen as the new coordinate system. And so these 3 plots are the scatter plots of the data using this combination of principal components. And then we can also get the r-squared, or the proportion of the variance explained by each principal component. Next, we can run the SL plot, which is the scores and loadings plot. Okay, so we have the scores plot and the loadings plot side by side, but this is only for the first 2 principal components. So continuing my other view of loadings as the new coordinate system. If we project our original data in the Cartesian, the original coordinate system, which center is all 0, we project those data to our new coordinate system, we will get the scores. And then for the loadings plot, here we can see the direction for each principal component. This is basically the linear combination of the variables. So ozone is 0.2 times principal component 1 minus around 0.4 times PC2, and so on. And then by running the SDEF, I already showed you earlier, this can show us the eigenvalue. And I just want to show you that running SDEF of PC3 is actually the same as applying the standard deviation of each column in the scores of PC3. Okay, as we can see, they are exactly the same. Okay, and then the next is loadings. I said earlier that the loadings are the columns in matrix V, so I tried to compare the loadings with taking the matrix V from the SVD function. Now, as we can see, we have slight differences, but maybe this is because we run the SVD function, and from which take the V matrix from the imputed matrix, the imputed data. While for the loadings, I guess the loadings here is from the loadings of the previous iteration. So like the last iteration before generating the imputed data. Okay, so what I'm saying is that perhaps we talk about two slightly different matrices after all, which explains the difference in these results. But I can show you that the loadings is indeed the columns in matrix V, and I want to show you by running these 3 lines. So we have a data set that is in R already, that is called rand U. So I run the PCA function using the SVD method, and then I also run the SVD function for the centered and scaled dataset, the rand U, and then compare the loadings and the matrix V. They are indeed the same. So yeah, if we change the method into SVDImpute, let's see. Yep, we still have exactly the same. Alright, now in line 127, I said earlier that if we project the data into our new coordinate system, we will get the scores, and here I want to prove that. So other than the NAs, we get the exact same result. Okay, I mean, like the NA is natural, only natural here, because we are multiplying the A, the original matrix, with the loading. So of course we get NAs. Okay, now let's move on. I'm going to run another PCA function, but this time for 2 principal components only. I just want to check the dimensions here. The dimension of the loadings is like the dimension of the reduced matrix V transpose, that is 7 rows for 7, that is for 7 variables, and 2, that is for 2 eigenvectors. Again, then the dimension for the scores, because the scores is actually the data set itself, but projected to a new coordinate system. This is the dimension. We have 8,760 rows. That is the total observation or the total time steps in our time series. And we have 2 columns, that is for the 2 principal components. And then the dimension of complete observation is 7 columns instead of only 2, because again, SVDImpute does the imputation for all variables. All right. Okay. And now let's see the imputation. So I'm going to show you the original data and then the imputation using 3 principal components and using 2 principal components. Okay, let's see, around January 22. That's the missing value we saw earlier. So the yellow is for the imputation by 2 principal components, and then the blue one is for the imputation using 3 principal components, and the green one is the original data. Okay, now let's see here. Like this one, this is January 23 at 6 a.m. The green, look at the green box there. It doesn't move along the blue and the yellow boxes. So this is telling us that this is where the imputation happens. Okay, maybe we should enlarge. Okay, so this is the missing period. And let's see. If we impute it using 3 principal components, this is what we get. We don't get a straight line, like if we use the basic imputation method, like for example, filling it with the mean or the median. So visually it looks nice. Okay, and now let's compare it with the 2 principal components. It looks quite similar. Right, now we can see that, yeah, they are indeed really similar. Sometimes the imputation using 3 principal components is higher, and sometimes the other way is true. Unfortunately, there's no valid way to scientifically measure the accuracy of the imputations, as we're dealing with real-life missing data. Of course, we could have trained SVDImpute on a complete time series, like on a complete subset first. If we want to do that, we take a complete subset, like maybe the end of the time series, and then we randomly take some values. So we create the missing values and then try to impute them using SVDImpute and see the accuracy. But I don't know, this might be an unpopular opinion. I sometimes think that we really need to lean more on the visual means. Just plot them out and see if they make sense. Like in this imputation earlier, it makes sense because it doesn't look like a straight line. It can't be a straight line. We cannot have a constant PM 2.5 for 3 days or even for 2 hours, right? It keeps changing. This is a dynamic world, so we almost always cannot have a constant value or like even really similar value. That's why like having straight lines doesn't really make sense. Yeah, I'm just stating my personal opinion here. Okay, and then this is, well, I tried a little experiment here, even though, as we will see in a minute, it's not going so well. So I tried using less variables. I tried using only PM 2.5 and PM 10 because these two are the most highly correlated. I mean, we want to impute PM 2.5 time series, right? And the other time series that has the highest correlation with PM 2.5 is PM 10, naturally. So I try to impute the missing values in PM 2.5 only with these two variables. And the imputation using that method is denoted with the pink line. Okay, now I haven't even zooming on anything, but we can already see some differences. Okay, anyway, let's look at this. Let's zoom in at the same period. Okay, yeah, so here, okay, let me zoom in even further. Okay, on January 22, we can see some straight lines, while the imputation by 3 and 2 principal components fluctuated a lot. Yeah, I guess, well, 13 is the median, or I mean the mean of the PM 2.5. Maybe that's why we get this imputation. We can check the center by using the center function. Yeah, as we can see, 13.25, that is exactly the mean, and that's why the imputation, the missing period is imputed with that mean. But if I remembered correctly, it's not always like this, actually. Wait, let me see. Like this one. On February 4, we have another missing value. Let me zoom in again so we can see better. Here, February 4, 11 a.m. This is the last hour before the missing period. Okay, so at 12 p.m., the imputed by 2 and 3 principal components show us, well, really similar value, 5 and 4. But for the imputed by 2 variables only, we have 16.8. We cannot say that this is worse, actually. But my point is that 16.8 is not the mean. And actually looking at this, we might... Wait, let me show you a better view. Okay, let's take a look at this. Actually, if we focus on the pink line only, it looks okay for this period only. Like, if we remove the pink line, well, I don't know, visually it looks okay. This is the original data. We can see the missing value. If we impute it using only 2 variables, we get it like this. But if we say impute it with only 2 principal components but 7 variables, this is what we get. Again, at the end of the day, we cannot really choose which one, but I will personally choose either the imputation by two principal components, the yellow line or the blue line, because in general, the imputation makes more sense. Here, I tried to take the ACF, the autocorrelation function, from each imputation and with the original time series, and we can see that they are really similar. So I guess this is saying that the imputed series is really similar with the original. I mean, like, if the imputation is really bad, then supposedly the ACF would be different as well, right? The same goes for PACF. We get really similar, even with a cyclical pattern here. We get to see that as well. So that's it for today's video. Thank you so much for watching. I'll put this code in my GitHub and Kaggle. If you are interested in learning more about time series analysis, please consider subscribing to my channel, Timely Time Series. I'll see you next time. Bye-bye.